Okay, good afternoon, everybody. Thank you for joining us. My name is 𝗪𝗂𝗥𝗧𝗨𝗪, and I'm the marketing manager for SIGMAXIM, a PTC partner specializing in Creo automation solutions. Welcome to our webinar on virtual master model. If you have any questions during the webinar, please press the Q&A button at the top of your screen and type in your question. We'll do our best to get to them at the end. I'd like to introduce our speaker today, Charles Farah, Technical Director of SIGMAXIM. Over the last 20 years, Charles has successfully delivered numerous implementations for our clients, ranging from technical configurators to design process automation and manufacturing process streamlining. He also worked at PTC for many years and altogether has over 30 years of experience with Creo. And today, Charles will be providing valuable insights into Virtual Master Model. That's our breakthrough framework for large and complex products in Creo. Charles presented this recently at the PTC User Group Summit, and everybody loved it so much we thought that we should repeat it here due to popular demand. So now I'll hand it over to Charles.
All right, so good morning, good afternoon, or good evening, everybody. So thanks, Maria, for introducing me. I don't have to do it then. So I'm going to talk about Virtual Master Model today. So this is not some new product that we have. It's basically something we've been implementing at customer well over 15 years. And it basically was developed by necessity for us the ability to build products that are to order, however, where it's too large or too complex for us to build them traditionally the way people normally build these, automate and build these products. First, let me start by introducing SIGMAXIM. So SIGMAXIM, we've been in business 2001. We're based headquartered in Boston, and we have operation in both Europe and Asia. We're a PTC software and service partner. And what we're known is really a very large implemented solution set that has well over 1 million applications running worldwide. Automation application, automating Creo worldwide, something that is quite massive because of the platform that we use allow us to maintain such a large set of applications. What SIGMAXIM does is basically automation. And automation, the way to view it, is eliminating non-value added engineering work in Creo. So we want to look at a bunch of things that take multiple steps to do, and we want to pretty much bury all that knowledge into an application that automatically can do it with fewer steps. Could be automatically one. So our methodology is looking at the different ways that people do automation. And because people requirements are so different, we end up grouping our practices into people who are doing basically ETO to CTO types automation, engineer to order, configure to order type product. And we call this one our on-demand product build. Is the idea is we can build automatically products in Creo from input without really user interaction by following rules of how to build these products. The other part is some customers of ours don't have this need where their product are kind of to order, but there's always rules and processes that they want to follow, and we can automate that. We call that one interactive automation. And out of this grew the need for us to develop this what we call virtual master model. The idea that we have very large assemblies, and these large assembly we require us to create them, create a problem that we have to solve, and we solve it this way. Us SIGMAXIM, the way we view ourselves, we are automation expert. That's all we do. We are Creo automation expert. What we implement, we're trying to implement stuff in giving people immediate ROI using building blocks. So no matter how large this automation, it builds on smaller building blocks that kind of arrive to the final result. So the scalability we view as infinite scalability. We can build and automate as big a product as possible. You're going to see that what VMM allows us to do in order to scale that large. And the most important point is that last point is the platform that we built on is maintained to every release of Creo. So that means once automation works, it continues to work with every release of Creo. And that's really key for us to be able to support such a large set of automation, over 1 million. We have to be able to ensure that anything that's working continue to be working regardless of version of Creo. And that's fundamental to how the system works. So the challenges. This is not the first time people are trying to make a automation for a product that are to order. So that means before in the 90s and probably, for Creo in the 90s and probably before, people are trying to figure out how to automate products that are to order. So most of the time, you're gonna try to solve a problem with the tool that you have. Us being CAD people, CAD users, we have the CAD, Creo, which means we see that we have the ability to do a big assembly. So therefore, we want to solve the problem by whatever tool we have, which is the assembly in Creo. So if you think about it, we can think about, all right, I can take every single part that I can ever be into this assembly in whatever location it's going to be, pre-build it ahead of time, and then throughout the year either have family table, program, notebook, model builder. All of them are based on this core that I have a large assembly. I want to overbuild everything in it and suppress what I don't need. So there's a saying in English that if the only tool you have is a hammer, every problem is a nail. And that's exactly what we see here, is that we have a tool that we know how to use, and it's the assembly. And I pretty much can set the problem to be fit in the assembly. And this is where master model got created. The overloaded master model approach got created. But that on itself, although solves the ability for us to think about multiple conditions and how they assemble to each other, so we can pretty much overload the model and know where everything relates to everything else. It creates problem on their own. PLM conflict, these master models themselves, depends what technique we use. If we end up with program, they have the same names. So as they vary, they are not really new model, which becomes kind of difficult to maintain in Windchill or any PLM system. The complexity of the models, that means over the year, as I want to maintain it, I have to maintain something and open models that are 100 times maybe bigger than what they're supposed to be when I'm using them. And the complexity and the time required for us to maintain stuff as the number of parts grow in them, and they are on top of each other, so they're hard to view, is exponentially harder than in a normal assembly. So then as we want to use them, regeneration time is longer. There's a lot more stuff than we ever need to have. And more important is the load time. So downloading models from PLM is the biggest penalty we can take when creating these to order product. And now we're downloading 10 times or more object than we ever need to have for this problem. So so this is where this solution came about. 15 plus years ago, we were confronting with this problem, and also with the problem that there are certain product where this whole approach of thinking about a master model, it just breaks down. It doesn't work. The combination is infinite. So how do we build a to-order product when the combination is infinite? Okay, so this is where we start. Okay, this solution came about. So the solution came about saying, okay, so if you think about traditionally what people are doing, they're overloading an assembly. So graphically, the way you can view it is that I have some product and I want to build in it every single option on top of each other that can ever be ordered, built up, following these rules. I was just going to overload the heck out of this assembly, and that's what I'm calling my master model. When I have an order that I need to do, like this to order product, assemble to order, configure to order, whatever product, engineer to order product, I want to suppress anything I don't need into arriving at this model. So So then you start thinking, is that what does this overloaded assembly actually get you? It only gives us one advantage and nothing else. It lets us know how things relate to each other. So now I know that a certain part is assembled into some subassembly somewhere using a certain mate, a certain alignment, a coordinate to coordinate, a a coincident surface to another coincident surface, etc., etc. So really, that's the only thing an overloaded assembly gives us. So we take this huge penalty because we are trying to gain one advantage, how things are related to each other. So our approach is that we really don't need to maintain this large assembly. The only thing we need to maintain is how the knowledge of how things relate to each other, this mate, align, coordinate to coordinate, coincident surfaces, etc. This knowledge, once I know that a certain class of part is assembled to certain other classes of part using a certain criteria of how to assemble them, I don't need this assembly anymore. And really, I can pretty much grab the object and assemble them as needed, since I know how they assemble. So for us, basically, we need to have the info. This is what we call the VMM in the VMM database. Is what we maintain is the info of how things are related to each other. And then the PLM system, Windchill, for example, maintain the actual part, contains the part that you are using or the subassemblies that are using to come together to make the final 100% two-order assembly. So this advantage, besides not having to maintain these massive assemblies anymore, it also gives us the ability to layer some external overlay of knowledge on top of that. So imagine that in your product, you have variation of this assembly based on maybe jurisdiction. Maybe different states have different codes that has to be maintained, or different countries have substitute parts that has to be coming into effect based on. So we can maintain these different additional layer of information on top of this information that is fundamental to how we're going to build that part, these assemblies. So that would even simplify even further that assembly itself, while keeping extra information kind of separated from the rest of the information that are how to assemble them. Other type of additional information we can layer on top of it are maybe certain part of the subsystem cannot be measured, cannot be defined just logically, but rather you have to look at the geometry in order to figure out how to do it. So those rules can be layered externally and on top of this virtual master model that we want to maintain, which is the core of what we're trying to assemble. So basically, this is kind of the approach. And out of that, usually when people come to us, either they have a problem where their product cannot be built up with an overloaded assembly like that, or most likely, they, in most cases, they've actually spent years trying to maintain these sub-assemblies, and it's very painful. So they're coming to us, say, how can we get it easier? So obviously, we don't want to tell them, oh, start over. And this model has taken years. These types of model, these overloaded model, has taken years usually to maintain and have it debugged and making sure it all works. So it has a wealth of information that we absolutely need, and we don't want to throw it away. So basically, that historical data, what we can do is extract it out. So we extract it out. It goes into the VMM database, into the VMM product, basically extract all of this information, understand what are the different classes of the of parts that you have in there, and how it relate to each other. So now that we know how it is, the PLM system is only maintaining basically the ingredients that are necessary for us to put them together. And this assembly is no longer necessary. This master model, this very large overloaded assembly, is basically, we took the essence of why we need it. Why we need it is this, and now all I have is basically a database that would look something like this. It's got different information in it, and that's really the essence of what we have seen there into this master model. So it's just the metadata of how things assemble to each other. So that's the first time, Then in the future, if we're adding some object, doing anything in there, all we have to do is basically, we don't have to grab the whole overloaded assembly. We grab just the minimum part. Like in this case, I have a new bucket in here that has to come into this assembly. So I'm going to go there and assemble it any way I want to. Very, very light model. It might have only 2 parts if we want to, or some subassembly and something that comes on it. So we need just the basic thing about how does it assemble to each other. And actually, if it follows the general rules, I don't even need that. I just have to name it and just say follow whatever rule you haven't before. But let's suppose this is an exception. It's a little bit different, and I want to add it to my model. So what I have to do is basically assemble it. And once I assemble it in, I'm just going to classify it. And by classifying it, I'll extract all this information, and it basically goes into my database, and I have a new entry in there that's going to have extracted how things work, where they are, etc., etc. Done. So maintaining that model becomes a simple task of assemble something, add something to it, remove something to it, modify something from it, and it's just extracting it, going into a database. I don't have to maintain any large assembly models to deal with it. It already understands how things are. Now, on a day-to-day operation, now that I understood how the part assemble to each other, on a day-to-day operation, we have usually a configurator. So that configurator could be something like what we call a characteristics configurator, something like Oracle CPQ, or there's tons of them. Really, there's probably 100 of those. And one of them is actually ours too. We have a web-based configurator. That's a characteristic configurator. We are telling it what are the characteristics of the assembly that we actually need. The other way you can build it is with the Windchill options and variant. So options and variant gives us a configured BOM and a variant spec. And out of that, we know what you are calling for and what you want to basically assemble. And we can actually have an extension to options and variant where we can add an attribute that will take options and variant from an assemble to order system to become more of a configure to order, engineer to order system, where the attribute basically tell us extra information for us to handle on the assembly. So once we have this, we basically start building, we grab the information of what's being called for, and we understand how they come together, and we grab the CAD objects from Windchill and just put them together. So something like that would be, here's a demo. Now, purposely, this demo I selected in something that couldn't be done with a overloaded assembly, because it has to be built from scratch, from the ground up, just because the combination is infinite. So in this case, this is actually coming from, the configuration is coming from SAP Configurator. And what we are doing is we're getting all the parts that has to come together and follow certain rules for building these units. So the ingredient parts is about 50,000 set of 50,000 parts that can be ordered however we want to order them. And now they're being called to a specific unit. These different unit goes into cabinets. These cabinet has to join together with electrical buttons, etc. Bus back in order to make a shipping unit, etc. And shipping unit go together into lineups. But as we build each one of them, we're also building drawings, footprint drawing, elevation drawing on the fly for each one of these objects. And at the end, we're also coming up with some analytical data that you see flash into these Excel spreadsheet, basically, where we're analyzing what's coming on here and giving these reports at the same time. Part of this is also creating a new part number. So imagine parts go into a backplate. Backplate has to have some cuts and some holes. So this backplate itself has to become a new part number where we have to also produce some manufacturing information all at the same time. But it's following this ingredient. But the core of it is this VMM model that is having a description of how things assemble to each other and where they go, and just go start building it. So and you clearly can see in here is the infinite possibilities where things are going to come together, and why we cannot, even if we want to, do a normal traditional virtual model, a virtual master model. We cannot, I misspoke, we cannot build a traditional assembly master model. We had to build it in this virtual master model where we understand how things are and we build from the fly, on the fly. So, okay, so this approach, the main advantage of it is, beside maintainability, is scalability. So we can, with that approach, build stuff even, building size, or things where it has to fit a footprint, has to fit some geometry that you cannot predict ahead of time, but you have to interpret and then follow the rules for it. So that's one. So the benefit, we kind of view them in in three different kind of buckets that we saw. The first one is these minimal base assemblies. So base assemblies, I saw you something that start from scratch, from zero, but in certain product, you might have maybe 30% that always exist and you start building on it. So we don't have to start from zero, we start from whatever makes sense logically. The assembly information is stored externally until needed, which means I never have to upload large assemblies and never use them. I'm only using what's being called. And now, since I am building stuff and building any deliverable as I need, I can follow the rules to build it. I can also build drawing or any other deliverable that is a result of that drawing, basically. And I have them show some other stuff there after. So the second thing is that the data is much more manageable. So in PLM, we only have the part or the sub-assemblies, the things that are not changing, basically. That's what they are, and they will come together. Naming convention, we can basically manage it whatever the PLM system allow you to have. So for example, you can create new part numbers, because so in the example I shown you, the back plate has to receive some holes or some cutouts. Therefore, it really becomes a new part number. So we are going to manage that and create them. And the components are basically fetched as needed. We are not gonna grab 10 times more component in order for us not to use them. We're only bringing from PLM what we are using. And that's really the time. This is the biggest time. So anytime we're building product to order, the download of the component that we're going to use, the download from PLM, is the biggest variable about the full time that's going to take to build this assembly. This is by far the biggest time penalty that we take. Okay, and the last point I want to talk about is CTO and ETO products. Since now we can follow rules of building them, the rules are external. It's no longer buried into these overloaded assemblies. It doesn't have to be just an assemble to order solution. It can be a configure to order and a engineer to order solution. That's why I said we can then take options and variant, which is designed to be an assemble to order solution, and add these attribute. And with this attribute, basically be able to automatically change and build new part numbers that will layer on top of it. So you take that product that is supposed to be assembled order and make it able to handle problem with engineer to order and configure to order. If some older variant were done and we can find them, we can actually fetch them. So we don't have to create everything from scratch. Stuff could be actually brought in. The variant contain only needed component, so there's no suppressed object. So now if you have a custom product, maybe 95% of it is one of those automatically built. You go open that assembly, you're never gonna end up with this problem where everything is hand together, and you start modifying stuff, and the whole assembly falls apart with a lot of regeneration error, etc. So it's just a assembly that is built as cleanly as possible from scratch. We don't have extra things that we're putting only to handle the variability. So let's look at a couple of examples. So so here's another example that also actually show you that it can't be, in this case, also built from scratch. Obviously, these examples I picked on purpose that could not be built with the overloaded approach model, because I don't want it to be thought, is there an overloaded model behind the scene that you're hiding from us, right? So think about here, I have a configurator. The configurator is picking a bunch of, an engine, an oil tank, stuff like that. So this is creating a fire pump room. So one of those rooms for fire suppression. So from the pump to the engine, the system can figure out the coupling based on torque and etc., power, etc. And then it's going to continue. We have inlet, we have outlet, we have required pressure, required volume. And out of that, we are trying to address them. So the configurator that came in up front did not know, it could not have figured out all of those, how they got, because you would see some things here are basically geometrically analyzed and figure out, you know what, the geometry won't fit in here. So I have to follow some alternate route of making a new branch. I have to add some valve, which means I have to go back and adjust my geometry, get these longer in order for these valves to fit, for example. It's calling, the system is calling for certain controls and certain oil tank. So for a certain jurisdiction, there is certain distance that this control has to be from the engine. So I'm going to flip it to the other wall. I'm going to go to this and move it to the minimum distance that's allowed to be close to the engine. That door has to be adjusted now that I flipped this one, etc., etc. And now that I have all the heavy stuff, we know where they are, I can now calculate and figure out where my structure is and build it. So as you've seen, that there's something happen here that we call geometric configuration, where the geometry is informing us about certain steps that have to be taken, and we can layer them out. Now, obviously, if the configurator, the upfront configurator, gave us all this information, we don't have to do any of that. We can just apply it. But in a problem like that, this is pretty impossible to do with the upfront configurator. There is a lot of geometry that has to be maintained. And once this assembly is built, now we can create the drawings, we can create any deliverables that we want to have to be seen. So what this one attempted to show you is that beyond the ability to understand how things assemble to each other, we also can make geometric analysis, and based on that geometric analysis, inform ourselves about what else we want to do. Whether what we informed on is where to create this structure, or whether we figured out that geometrically here we need to start another branch, or the distance between things to each other, etc. So that's another example of virtual master model where it's assembly stuff to each other, but also it's adding an extra layer of information that allow us to do these additional changes. I'm going to run another demo in here that shows basically similar stuff. So here we're building basically a building size. It's a tower, basically. And we have to build the structure. So the requirement is calling for certain things to happen, but then in order to speed up this whole implementation, we can geometrically analyze how things are and start building them. Like you see, it's calling for certain braces. The lengths of these braces, we can just calculate them geometrically. We don't have to tell the system exactly where to place it and where it has to be, you can say, well, follow it from a certain distance and see where it hits, and from there you just go and build it. And this is how we continue to build. So now this is being such a large assembly, we cannot build everything with the geometry be in, you know, in the same session. So we're handling that session with a on the fly simplified reps, basically. So we're building these on the fly simplified reps in order to make sure things can be loaded in memory as we build this configuration, and it continue to build. So as it continue to build, we are figuring out where, you know, what we need to load in order to calculate the rest, and, you know, building it. So we can figure out the structure that way. We can take all the outside and build the skin of this building, and then whatever areas we need in order to hang componentry, we can have it in order to basically start assembling the componentry as it's there, and then removing it from the simplified reps and building a different type of simplified reps to continue using it. So that's another, and that's basically the end result will be something like that. So of course it will take time to get there, but it just builds. So this in a nutshell, what the virtual master model is. So it's introducing you to this concept that you don't have to maintain very large assemblies. The assemblies that are to order, the overload assemblies like this is not necessary. Once we have them, or all that we need, we can basically extract all the information that we need, and now it's metadata. And from there on, we build on the fly as needed. And that concludes my presentation. I think we do have some questions, so I'll open it to, and anybody who has any questions, please type it down and we will tackle them one at a time.
Okay, so one question that was asked, does it work only with Windchill?
Good. Yes. So no. So what it works is only with Creo, but the PLM system can be anything that you want. What we're getting out of PLM, like whatever system, is that we want to be able to download what we need. So to download what we need to have some call that gets us what we need. For us, with Windchill, we already have those calls, so we don't need integration with any other system. With any other PLM system, the same way that in Creo you need a third party to integration to your PLM system in order to in Creo go and open an object that's coming from your third party PLM system. The same is for us. We need to have access to that third party integration in order for us to download the objects from the other system. So we don't have that third-party integration except to Windchill, but we can use somebody else's integration in order to pull the object from the other system.
Okay, the next question is, how do we extract all the component/subassemblies level parameters? Is it manually extracted?
Yeah. So I think maybe I understand what the question is all about, right? So you probably part of extracting this parameter is that you want to do some logic. You want to either report on them somewhere, or you want to also, you know, use them in your logic about how to assemble stuff, and that's fine. So maybe in those parameter is the class of object that you have, and I've seen that. So in order to know how then to assemble it, then it is perfect. So we can, so the system is able to actually read parameters in parts or assemblies or sub-assemblies and whatever. So we're able to read what part parameter, we can read them all, or assembly parameter, and then we can apply logic based on that. So basically we have search, we have commands that do searches, search model params, and what is it that we're searching on, and we get in it. And part of that now is to figure out what the logic is. So the logic then could be anything. Like, so I've seen, for example, where these parameters are basically the classification of parts. So in order for us to know what that part is, we have to go and look at a certain parameter. Now, there are other ways of doing it. The database itself can tell me what that part is, what class of object it is. But if it's already implemented, where it's the parameter in it that tells us what is that classification for that part, then that's what we would look for. So you have a part being called for, you go open it, you figure out its parameters, some parameter class, for example, classification. And out of that, now we know what it is, so we can go and figure out how to assemble it. Yeah, we can do that.
Okay, the next question is, how are errors flagged and resolved during the building of the VMM?
Yeah, so it's actually so interesting. Usually when we build stuff like that, so I'm gonna even open this one, and hopefully I picked the right one, because yeah. So when we do these types of assembly, like I just said that this one has a in real life, this is obviously a demo, but in real life, the amount of component that could be assembled in here is about 50,000 component, and some of them can be orderable, and they are like from the 1950s, and you can still order them and assemble them in there. So most likely, these component don't even have ProECAD object associated with them. So what we have to do is, usually when we do stuff like that, we are tracking kind of error and logging error. So the error could be that, okay, I try to find this object doesn't exist. You're calling for a certain part that need to be assembled in here, and this part does not exist. So what do I do with it? What I have to do with it is, I'm just going to keep it in empty. I know it's being called for, but that's a punch list for somebody to deal with it as a ETO or a custom kind of a process part that will happen after. So I don't want to fail that whole assembly just because, some part of it did not show up, or maybe it's corrupted and I cannot download it and to use it. So if a failure happened, usually we want to report in a log file for somebody to actually maintain, but we want to build as much as we can and let it happen. Let the other issues be dealt with as a second step by somebody. That's the best we can do. There's nothing we can do other than that, right? There's another concept that we do a lot, which is obviously to have a large automated assembly that can be built all the time. It needs a certain level of consistency in the data. And humans are pretty lousy at consistency. So humans aren't really very good to build consistency in data. So if you give me 50,000 parts and tell me, well, make sure these classes of part have a certain name for the surface in order to mate it to it, etc. If you put 100 people on it, you get a bunch of inconsistent data. If you put 200 people on it, you're not going to get it any faster and any cleaner. You're going to get even more inconsistent data. So in these types of approach, we have something where we build basically automated sifter to ensure that the parts that has to be part of this configuration have already ran through a sifter that gave us an indication about which ones are consistent, which ones are not consistent. So we want to use automation to ensure that our automated system at the end works correctly. So if you give me 50,000 parts and I know what their classifications are, and I know what each classification require as far as references, for example, I sift through them all, and I want to get the list of only the acceptable ones to go in. So now we want to fix something. We are fixing only the ones we know which one are good, that's going to work, which one will not work. And even those that are not work, we can use automation to actually fix them. So maybe the name is not right. But most of the time, we don't want to change these parts because these parts has been released a long time ago. So we don't want to just say, oh, just change them to be consistent like the rest. We want to record the inconsistency. The inconsistency itself will be part of the virtual master model since we are not able to change the original model itself. We want to record what is the actual part that has to be assembled. That becomes exception to the rule of how things get assembled. So there is a lot of layer to this whole thing. It's a pretty interesting question, actually, that I can go on for half an hour about it, and that bores everybody. Yeah.
I did get a question, Maria. So the question I received was more about the measure and build and what type of parts would be used ideal for that.
Say the question again, please.
Measure and build. So are you doing some type of automated measure and build and aspect?
Okay. Yeah. So, and of course, I'm trying to, obviously I'm trying to understand the question. So, that question might have arisen from this, right? When you saw this, right? Where it's saying, okay, what's happening here? I need to do something else, right? So we call this basically geometric configuration, where we are doing, or actually geometric validation, where we're doing some validation using the geometry in order for us to do further builds, right? Further things that has to happen, right? So obviously we have to measure in this case, and I wonder whether this is what you are leading to. So part of what we're building here is not just blindly taking what the configurator told us to build. There is an extra layer of logic that is implemented on top of this. And that extra layer of logic is saying that, okay, in certain instances, while you're building this, you need to test certain condition. And with these conditions, if they are not met, you need to do something else. And that logic can be as elaborate or as simple as we need it to be. But there is an extra logic that layers on top, where we're measuring the condition, figuring out what we have, and doing something with it. Hopefully this answers this question. Otherwise,
yeah, it's good. Thank you.
Yeah. Okay. Good. And
does anyone else?
And if somebody asked the question and my answer isn't misunderstand, just shoot the question again and say I misunderstood it. Right? I will take it in a different angle. So.
Does anyone else have any other questions?
Okay. So.
Okay. Well, thank you, Charles, and thank you all for joining us today. We hope you gained some valuable insights to enhance your Creo design processes. Everyone who signed up will receive an email with the webinar recording. If you don't receive it, let us know. If you have further questions or would like additional information, just reach out to us at info@sigmaxim.com. You can always also reach out to us on LinkedIn. And thank you so much. We look forward to seeing you again at our next webinar. Have a great rest of your day.
Thank you.